me, right?
Yeah.
Okay, let's start. All right, so let's look at question 27. Okay, this one I think I never give the answer for this question, but it's okay lah, not too difficult. Okay, so we talk about photoelectric effect, right? So for photoelectric effect, remember there is your first thing you have your basic equation. Remember the energy of your photon is used to do two things. Okay, so you have energy photon, this is HF, right? HF is used to first overcome your work function. Okay, and then whatever excess you have becomes kinetic energy, right? Let's say you have your surface here. This mode function refers to the easiest to remove electron, let's say just below the surface, right? You want to bring it up this way to here. Okay, this energy here is your work function, right? So just take note. So whatever excess you will become your KE lah. So of course, if you have electron that's buried deeper down here, right? For it to come up to here, it comes up, you need some raw energy first. This is delta E. Come up to here, you need to have work function. Okay, so obviously this guy will not have so much KE as compared to this one here. All right. Then this graph here. Okay, so this is for the individual electrons. But then when you talk about a piece of matter here, so let's say you have your method, how to draw it? Yeah. So your circuit, remember, looks like this. Uh, okay, so you connect this circuit over here. You have a variable resistor, a variable power source like this, right? Okay, and you have your incoming radiation coming in this way. Electrons are coming out from here. Okay, so I can vary this value here. Okay, then of course I put a milliamp emitter in the middle here, and then also I can measure the EMF lah. So I can measure EMF just directly like that. Okay. So this one. Remember if you for your photons, right? For your photoelectrons, right? They have to absorb. They can only if you will have photoelectric effect only when they take in one photon and is able to come out. Because remember your electrons will want to stay at the lowest possible energy level. If it takes in energy, you want to give up at its level. So it cannot accumulate the energy from different photons. Okay. So what's happening here is that once you have so this first portion here talks about whether or not you have photoelectric effect in the first place. Are your photons energetic enough for that? Okay, so once you get photoelectric effect, of course, what happens is that when they come out in this setup here, right, this plate right now, this is negatively charged plate. So your electrons, when they come out, right, there's no issue of them reaching the other side because this guy is positively charged. Okay, so here, what I'm trying to do now is that this value here, this occurs on this side of the graph lah. So you will see that your current will peak. Your current peak because it is dependent on the number of photoelectrons per unit time. This current here, this is number of photoelectrons per unit time. Okay, so this is what we know lah. Okay, but if you change this plate to become a positively charged plate, that means I go to the negative EMF here, right? Then some electrons will start to turn back. Okay, once this becomes a positively charged plate, right? This portion becomes kind of like if you think in terms of like say gravity, this becomes an upslope by that. It's like trying to roll a ball upslope. You want a ball to reach out the slope, you need to push it, give it enough speed at the start lah. So you will start to have some of the electrons with lower, some of the photoelectrons with lower KE, right? Being forced to turn back already. Okay, as they turn back, right, the number of photoelectrons that reaches the other plate per unit time will also drop. Okay, so that's why you start to have your current dropping. Until you come to the point where even your most energetic photoelectrons will drop, right? Let's say this value here, this is EVS. This is so-called your stopping potential. And your stopping potential here, right? This is equals to, okay, so it's just VS, not EVS. Okay, it's EVS. Okay, so we know that stopping potential, this is yeah, fraction. Stopping potential, or let me opposite. Okay, so this one, EVS is equals to KE max. Okay, So these are some of the things that will affect lah, right? Okay, so let's look at the question now. Okay, so I do the experiment. I will get this graph here. Okay, so this one I'm getting photoelectric effect, yeah. So it's just so I'm getting this one here. This is the graph currently. Okay, now I repeat the higher density. Same frequency radiation. Okay, if I'm using the same frequency here, right, that means my energy here, this one here, this becomes work function plus EVS. Okay, so I get this form here. So if I don't change my F, I will not affect my stopping potential. Okay, if I don't affect my stopping, if I don't affect my KE max here, right? If my KE max doesn't change, okay, since I don't change frequency, my KE max is not changed. Therefore, my stopping potential is not changed. So the graph should still terminate at the same point. The stopping potential should be the same value. You will not get more. You will not get photoelectrons that are more energetic than what you have beforehand. So to stop them, right, requires the same stopping potential. Okay, but you increase intensity. Okay, so increasing intensity is that basically you are having more photons coming in to the material. Remember, your photon and electron interaction is a one-to-one interaction. So you want to free up, for every electron you want to free up, you need to have one photon available for it. All right, so that means if I give you high intensity means, okay, let's draw. So this one means you have more, okay, so photon, yeah, okay, so number of photons will increase. That means number of photoelectrons will increase as well. So the number of photoelectrons increase, right? Per unit time, you're going to get a higher current over here. Okay, so the best answer here is A. Huh? So I went a bit more to give you a quick overview of your photoelectric effect. Quantum, don't please study quantum. It's like there's no way it won't come out. It's like and there are many parts, so you need to be quite familiar with as well. Yeah, any questions? Anything you want to clarify about the photoelectric effect concept? Don't have, If you need to ask question, you can type, Okay. And next one is X-ray. Okay, so X-ray again, so remember photoelectric effect is having photons be incident on a piece of metal, okay, then free up your photoelectrons, right? So for X-ray it's the way around. X-ray we bombard your piece of material with electrons. Okay. So what's happening now is that, okay, what I do is that I have usually I will have a heated coil wire. Wire. Heated coil wire. So again, I set this up. Okay, so from here, right, you're going to have photoelectrons coming. You're going to have electrons coming out this way. Okay, let me zoom in a bit. So this is a coil. Okay, electrons coming out. These electrons are going to be incident on a piece of metal. Okay. So when that happens, right, you're going to this electrons, remember they all have kinetic energy. Yeah, this energy has be will be lost as it comes to the metal lah. So you can lose in a few ways. You can either, okay, we within the material itself, remember, let's say your electrons, the atoms inside your metal, right? They all have its own energy level. So this is you have different energy levels, right? Let's see, so this is E1 all the way to E3. Okay, so let's say you start here, right? Over here. Your electrons can become, okay, your electrons within the metal can be excited, can take energy from the incoming electrons over here. And when that happens, right, you will become excited. Okay, but this higher energy state, remember, this is not a stable state. So you will want to let go ASAP. So when let go, right, you can release in a few ways. You can, once let's say it's come out to E1 to E3, right, it can drop down, it can drop straight, or it can drop like this, and then like this. So for each drop, right? So let's say it makes a drop. Okay, let's do it outward. Okay, so let's say it goes up to here, all right? Then when it drop, right, you come down here, you release a photon coming up. Okay, make one more drop, right? Another photon will come out. Okay, so this is how you can get your X-ray photons to emerge from your target matter here, lah, right? Okay, another way is that these electrons, as they go past, let's say if you zoom into this piece of material, say that if you just imagine your material, right, it is basically a lot of positive ions here. These electrons, as they go in, right, electrons as they come in from outside, they go in here, they will get slowed down by they get attracted by your positive matter ions here. As a result, your electron might get deflected, you will lose some speed and then therefore lose some Ke as well. So when it loses Ke, again, it has to throw out the Ke, the form of a photon as well. Okay, so you get a curve that is, yeah.
If you for that, if they lose
Mm.
Ke because of being attracted to the positive
Uh-huh.
protons in the metal, what about the
Uh,
positive protons in the air?
positive protons in the air. What do you mean?
Yeah. Like, wouldn't they also lose
Uh,
Ke while traveling across the air since there are atoms with positive protons like in the air?
y- it's possible. It's possible. Not
Oh,
not 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 entirely possible. So usually these kind of experiments, you want to make sure that this area is a vacuum lah, as much as we can.
oh,
Yeah,
okay.
yeah. So I was thinking you were gonna ask about the alpha particles being ionized as well. I was thinking about that lah, but that one can come in later. Okay. So anyway, once you have this, right? Yeah, I don't have a graph here, but if I scroll down, I'm sure I can find something like this graph here. Okay, so remember, this whole curve here. This whole curve here is your breaking radiation, like that. Okay, so you're gonna have your electrons. This represents your electrons losing different amounts of kinetic energy, and then this energy has to be released as Ke lah. Sorry, as a photon lah. So there's a maximum. You see, as the minimum wavelength here. Minimum wavelength here corresponds. Remember, if you talk about photon energy, right? This is E equals to HF equals to Hc over lambda. So if I have a maximum Ke, remember photon gain energy from my accelerating potential. So I have if I set up the potential QV, right? QV, this will give me my Ke max of my of my incoming electrons. And then that means this will correspond to a HF max, which will correspond to a HC lambda minimum. Okay. Then these peaks here, these are your characteristic wavelength of the metal. So you can use this. So basically this is your breaking radiation, right? This is when your electrons just slow down as per normal. This one here is, let's say, when you cause your electron inside the metal to get excited out from, let's say, a low energy level come out to the next level. Let's say I just draw some energy levels here. Okay, so let's say if I go from here, I come down, drop here, right? This drop, right, may correspond to one of the peaks. This drop may correspond to another peak. Okay, so these are the more common energy these are the basically the allowed energy transitions this piece of metal. So they have a higher chance of occurring. Okay, and because of that, right, because of these peaks, right, you can essentially tell what kind of material it is. Okay. So then we talk about K lines and L lines, right? K alpha, K beta lines, right? So we talk about the lowest energy level. This is E, so this is E0, E1, and E2, right? So on and so forth, right? So if we drop to here, this drop here, this is a K alpha line. This is a K beta line. Okay, then if I draw one more energy level above for you, okay, so that I can have more drops, right? So let's say I drop to, so any level drop to the ground state, this is a K line. Okay, then you have the next step, okay, which is not that hard to remember, but I wouldn't say it's important no. Okay, so this one here, anything drop to the second lowest energy level, those are your L lines. Okay, and then this is your L alpha, this is your L beta lines. Okay, Yep. So this basically, when you look at a piece of material, right? If you can plot or you can recognize all its distinctive lines, right? Then you can kind of know what kind of matter it is. So if you look at this, right? The biggest drop here is actually okay. This, let's say these two are both K lines, right? You will see that this guy is your K alpha. This is your K alpha. This is your K beta. Okay, because remember, higher wavelength means lower frequency, means lower photon level, lower for photon energy. Okay, so this one is this drop here. This will correspond to your K alpha. Okay, then you have your L lines, right? L lines will be somewhere here because L lines, right? Remember, this is a log. This is kind of like a log scale. Okay, so this drop, anything drop to lowest level, right, will be higher than anything dropping to the second lowest level. Okay, so your L lines will be somewhere here. All right. Then this, remember, this graph is a measurement of intensity. So this is measuring how many photons of this particular wavelength are being collected. All right. So this is it for the theory for X-ray. So let's try this question for X-ray. Okay, so X-ray produced when electrons are accelerated from rest by a PD. So this is your accelerating potential. They collide with a metal target. Minimum wavelength X-ray produces lambda naught. What is the minimum wavelength produced if the momentum of the electrons is doubled? Okay, so I might need more space over. So let's just start a new page here. Yes, start a new page. Okay, so this is question 28. Okay, question 28. Okay, let's look at what are you supposed to ask. They are asking for minimum wavelength. Okay, so for this, right, we know that we start from our accelerating potential. So this is EVA, okay, accelerating potential. Okay, this is equals to Ke max of your electron, of incoming electron. Okay, and this is equals to Hc over lambda minimum. Okay, so basically your relationship is between your Ke max, your Ke, and your Hc over lambda minimum. Okay, so from here, let's look at, okay, then now we double momentum. They never say double energy, so be careful. So if I double my momentum, right, let's see how it happens. So see momentum, right, we know P is equals to mv. Okay, but then from here, okay, I'm going to not talk, I'm not going to derive this for you, but you can see that your kinetic energy is equals to P square over 2m. Okay, so basically Ke is proportional to P square. Okay, so that means if my P2 is 2 times of P1, right? That means my Ke2 is equals to 4 times of Ke1. Okay, so my kinetic energy quadruples. Okay, if my Ke quadruples, right? Then now that is okay. So if I do Ke1 over Ke2, right, is equals to Hc lambda. What they give us for this one? Lambda naught, right? Original. Lambda naught over Hc over lambda 2. I want to find lambda 2. Okay. So this will be 1/4 equals to lambda 2 over lambda naught. Okay. Right. So that means my lambda 2 is equal to lambda naught over 4. Math, right? Yeah, correct. Okay. So this answer. I'm being consult. Sorry. Go further away. Stop talking. Sorry, I have to shut some colleagues up. Sorry. Yeah. Okay, can. So this is question 28. Okay. Hmm. Can any issues? 28. I show the working again. Long cell working lah. Yeah. Okay. Where my pen? Okay, next we have go for it. Okay, go for it. Rutherford alpha particle scattering experiment. Alpha particles are directed at a thin goal for it. What is the direct deduction from the results of the experiment? Um, Nothing to do with the alpha. We already know that alpha is positively charged. So this is our question. No need to think about alpha. Okay, because we already know alpha is 2 proton, 2 neutron at that stage. Okay, and then we also don't know, this does not tell us that the proton number is 79 lah. So the only answer is C. Okay, so this one, remember for alpha, for Goldfoil, you can look at three things. Remember, this is your Goldfoil. This is your Goldfoil, AU foil. Your alpha is coming in this way. Okay, most of the alpha will go straight through. Most of them go straight through, about 97% of it. Okay, some of it will curve. That will curve to the side like this, etc. Okay, this is about roughly about 2 point something percent. Okay, 2%. Some of it will come back. It will turn back. So this is less than 1%. Okay, so since most of your alpha particles will go straight through, right? This tells you that your atoms are essentially empty space, mostly made out of empty space. Okay, because if you zoom in, right, your nucleus is here. This is the nucleus, and then basically you have your electrons at the side like that. Okay, so most of it here, these are all empty space. Okay, your alpha particles have a lot of room to go through. Of course, if they pass near to your gold nucleus, then you start the curve, right? Okay, you should be able to draw the path as well. So remember, the closer you are, the stronger the electric force acting on you. Okay, so if you go somewhere further away, right, it curves down like this. Okay, this curvature has to be kind of measured from the center here. So if your particle is here, you need to kind of curve it out this way. Then if you're closer, right, then the curvature will be much sharper. Okay, so these are the possible paths. Then of course you go head on, right, then you will just turn back. Okay, so this case the answer is just C, right? Okay, 29. Okay, moving on, so no issue. Okay, nuclear fission reaction. So you are given this reaction, you have uranium that is fixing 1 neutron. So this 1 neutron coming in will basically convert this uranium-235 to become uranium-236. There's a missing, there's an intermediate process here we never write about. This is basically that's uranium-236. Okay, uranium-236 is already unstable, but then because your incoming neutron brings in kinetic energy as well. So this makes it even more unstable. Okay, so this is a very this uranium-236 is a very temporary step before it goes on and just breaks down to give you your krypton, barium, and 3 neutrons. All right. So remember, when it comes to nuclear fission, right, we always need to think about, we should also think about energy lah. This one basically, right, this is like this one goes back to your chapter 3 dynamics when we talk about collision. Remember, inelastic collision is an explosion happening in reverse. So we have to be mindful that when, let's say we only have 2 masses coming off, right? Let's say we have 2 masses coming, let's draw 2 random masses, 2 masses like that, okay? They explode, they come apart from each other, right? You notice that because of conservation of momentum, let's say this guy or this mass at first is at rest, right? When this one wants to go out this way, the other one has to be along the same lane as well, same line as well. Okay, in order for your momentum to be conserved. Okay, so if you have one of them going out this way, the other one will have to be this way. Okay, for conservation of momentum. All right. So if you have a third particle, here, right? Let's say third one here, right? Let me draw another diagram. Okay, let's say I have a third particle involved here. It's like this, and like this. Okay, when they separate out, right? You cannot have a case where, let's say, for example, you cannot have this. You cannot have this. This one won't be able to work. Because if you have this, right, realize that these two fellows only have horizontal momentum. This one has some vertical downward momentum that is not cancelled off by any of these two momentum. Okay, so you cannot have two of them in this straight line, then this guy is here lah. This is similar to the question where I say that you have a line, you hang a weight there, right? This weight here, right? This line cannot be completely horizontal. You end up being like that. Okay, so same thing here. So over here, right? End up what happened is that they have to take on a slightly more vertical momentum, right? So yeah, these are things to take note of, right? Then remember when we talk about buying energy, right? The way I like to think about buying energy is that buying energy is essentially how much energy you need to remove, how much energy you need to separate your nucleus into its individual individual neutrons, right? So the way I like to think about it is that this is a pit, okay? How much energy do you need to take out? You need to free this proton. So this is basically this value here. This is our binding energy per nucleon, right? Okay, so you need to supply this amount of energy for it to come out. Okay, so you want to make something more stable, right? What you do is that you dig a bigger hole for it. You dig a bigger hole for it. This is delta E. Okay, so you want to make something more stable, right? You throw out this throw out some energy first. Okay, remember energy can be this in nuclear, right? Energy and mass can be converted to each other. Okay, so I basically throw out mass. Okay, I lose mass, therefore I lose energy. Once I lose energy, right? This it will increase the buying energy per neutron. So it means you need more energy to take out your neutrons. Okay. So back to this question, right? They want you to find what's the amount of energy released per direction. They gave us the buying energy per neutron. Okay, so this is the reactant, this is the product, this is the product. Okay, so since this, okay, I think because we are experienced with this, we know that this reaction will release energy. So energy is released in the KE of your reactants, and then the three neutrons will like KE. If not enough to carry, right, then of course you're going to have some other form of radiation, like usually gamma. Okay, so for this, right, we're going to compare the binding energy of the reactants first. Compare it to the binding energy of your uranium. So since this reaction is supposed to give out energy, right, we know that the reactants, the product, right, the binding energy, the total binding energy should be higher. Okay, so let's try. Let's try out this one first. I think this one is good to spend some time writing it. Okay, so let's write. We're going to write difference in binding energy. This is basically binding energy of krypton plus binding energy of barium minus the way binding energy of uranium. Neutron don't have, because neutron is just single neutron, so there's no binding energy involved. Okay, so we submit the values. So this is krypton is 8.7 multiplied by 92. So 92, 8.7 plus barium is 141, 8.33. Okay, minus the way uranium, 235, 7.59. Okay, so let's see this calculation very quickly. So 92 times 8.7 plus 141 times 8.33 minus 235 times how much? 7.59. 7.59. Okay, so I get 191.28. So 191 MeV. Okay, so this one here, this 191 MeV, right? This is the total energy that's being released. So this energy, right, it can come in the form of this will give you your Ke of your barium, Ke of your krypton, plus Ke of each neutron. Okay, if there's a need to, you can also have gamma as well. E gamma. Okay. How do you know when it's okay? How to phrase it? Is there a maximum amount of energy that can be carried by, let's say, like your neutrons? Is there a maximum amount of K that can be carried? Anyone? Is there a technical limit? How much can be carried?
The speed of light.
speed of light. So I think we talked about this during the time trial lah. Okay, so we look at the energy, right? So if we find Ke of a neutron, in this case is half mass of neutron times V squared. Okay, so then this is equal to some value. But you realize that this V here, right, this is limited to C, speed of light. Okay, speed of light. Okay, so there's actually a maximum Ke here. Okay, so you can basically half mass of neutron and multiply by 3 times 10 power 8 square. Okay, so if we keep on increasing the amount of K that has to be carried, right? Eventually you come close to this value here. Once you come close to this value, then you got an issue already, because that means remember your neutron or whichever mass, right? You cannot go past the speed of light. So there's a maximum here. Okay, but usually in the first place, it's hard to throw all the K here. So usually if the number gets too big, usually there's no real control to say, oh, definitely this one will have three neutrons and only three neutrons. It's also possible for it to give me some gamma as well, to just basically shell the energy. Okay, so just be mindful of that lah, right? Okay, so this is 20, 30, yeah. Okay, so this one here, again, going back to X-ray, going back to photoelectric effect. So I should just double all the photoelectric effect question first. Okay, so I have wavelength. Okay, I have metallic surface X. Okay, that is evacuate tube. That means it's a vacuum. Use wavelength 275 nanometers, causing emission of photoelectrons collected as adjacent electrode. So X is here. Okay, so X you can see X has a higher VF. Vs of X is larger than Vs of Y. Okay, so remember higher Vs here, let's write out the equation again. So this is HF, energy of incoming photon, equals to work function plus Ke max. And this is equals to work function plus EVS. Okay, HF equals to EVS. Okay, so if I use the same wavelength and I get this one here, I can see that if I make this guy bigger, this will become smaller. Okay, this will go closer to 0, right? Yep. So here, right, I can see that because my Vs, okay, that's right here. So because stopping potential for X is larger than stopping potential of Y, right, I can therefore conclude that the work function of X is larger or smaller than Y? Smaller than Y. Are we okay for this? So if I have, remember I'm using the same photon. If I'm using the same photon, right, and X is harder to stop, right, that means for the photon energy, right, a smaller fraction of it is used to overcome work function of X. Okay, I think I missed out one line here. So let's just, okay, so let me erase this out. Okay, so therefore, because Vsx is larger than Vsy, so therefore, EVS of X is larger than EVS of Y, which means Ke max of X larger than Ke of Y, which means work function of X is smaller than work function of Y. Okay, so I'm looking for a matter that goes up in terms of work function. Okay, so the only answer here that will go up, yeah, work function go to a higher value, which is the best answer. Sodium to aluminium. Yeah, do something wrongly, yes. Yeah. Something wrongly, yeah. Answer for this one. 7. I didn't give answer for 27. I got the same problem as the copper drop to aluminum. Ex. Ex larger than Vy. X larger than Y. X larger than Y means Vs, EVs larger than Y, Ex larger than Key. That means work function of X smaller than work function of Y. So it should drop. So I must find a pair of values where it drop. Copper to copper, no. Copper to aluminium, yes. This one will work. Because this one, copper is larger than aluminium. Sodium is smaller than aluminium. Sodium is smaller than copper, so answer is B. And you got things just ask, right? Okay, 28, I'm gonna skip. Okay, 29. Okay, 29. So just now we had a question where we measure energy release in a nuclear reaction using binding energy, right? And another one is to compare the mass. So if your mass of your product is less than the mass of reactants, that means this energy is an exothermic one, is releasing energy into the system. Okay, so in this case here, okay, so let's look at this one. We have two deuterium nuclei produces a nuclide of helium and a neutron. Reaction liberates 3.27 MeV of energy. How does the combined mass of the deuterium nuclei compare with the helium mass and these products, right? So I know for sure because this is the release of energy, right? So I know that mass of reactant has to be larger than mass of product. Okay, how much bigger? Okay, how much bigger? So it depends on how much energy. Remember to convert this energy into mass, right? To mass effect, right? We go for the famous equation E equals to delta M C square. Okay. Make sure that this one is in terms of your SI unit. So this one is in joules. This one is in kg. Very important. Okay. So do the conversion. So find delta M. Delta M is equals to 3.27 MeV times 1.6 times 10 negative 13, okay, divided by 3 times 10 power 8 square. Okay, and they want it in kg, so don't have to convert again. So let's calculate it out. So 3.227 times 1.6 exponential negative 13 divided by 3e8 square. Okay, so this is 581 times 10 negative 30. Okay, so 5.81 times 10 negative 30 lah. So best answer here is A. Okay, reactants is 5.8 times 10 negative 30 kg more than products. Okay, because this reaction liberates energy. So liberate means you lose, your binding energy increases, your mass decreases. Okay, so be careful about that. 29, 30, not selected, but I think we can briefly talk about it. Remember Q, this is your binding energy per nucleon. Q is the most stable point here. This point is roughly about 56, which corresponds to iron 56. Okay, so your nuclides all want to become as stable as they can. So if you are here in this range here, right, you want to fusion together to go towards Q. If you are here, you want to fission, you want to break up to come towards the mass that's closer to Q. Okay, so let's look at the statement which is not true. Energy not true. Energy is released in nuclear fission. Let's underline the stuff. Nuclear fission reactants from nuclei in P, in region P. So not true. Release in. So if I do fission here, okay, so this one seems not true because here, if I want to go release energy means that I will go up to higher by energy per nucleon. So to go from P, if I want to fission, I will end up going from P, fission, I'll go downwards. Go leftwards and therefore going down. So A seems to be wrong, but let's look at it in a while's time. Okay, so let's look at B now. B says region Q more stable than in region R. Q is more stable than anything else. So what's coming up? Okay, so this one is confirmed true. If it's confirmed true, means that is wrong. Okay, so nuclear fusion reactions from option C now. Fusion reactions from P produce nuclei closer to Q. So Q, okay, P is over here. If they fuse, then they come closer to Q lah. Yeah. So this is true. Therefore, it's also wrong. Okay, binding energy per nucleon increases more significantly when nuclei in region P undergo nuclear fusion reaction. Okay, so this one, the comparison could be, is not stated here. It's saying that, okay, when P fuses, you will get more binding energy increase per nucleon compare when R fission to here. Okay, this is purely by the increase in the, you can look at the gradient here lah. Okay, for small increase in your number of nucleons, right? This has a big jump compared to, let's say, over here. Okay, so again, D is wrong, so answer is A. Okay, so you want to change this statement to correct, right? Then this one will become fusion. Okay, then this will be correct. Okay. And okay, we move on to structure. Okay, so after you look at this question, okay, students suggest that one possible nuclear reaction is 56 iron, I56 add one neutron, then become fluorine and chlorine. Okay, so explain why this reaction will not result in an overall release of energy. Okay, the key here is that you are dealing with iron. Okay, remember your stability graph. Iron 56 is the most stable already. So if you start with I-56, no matter where you go, right, you go left, you fuse to become bigger. Sorry, you fuse to become bigger and therefore go right? Or you fission to become smaller, right, go left, right? You will reduce the binding energy per neutron. So when you reduce the binding energy per neutron, right, that means this reaction is, in chemistry, they call it endothermic reaction. You will need to supply energy for this reaction to happen. Overall, you need to have net input energy. Okay, so we look at answer key for this one here. This is talking about the stability part. All right, so if you go from I-56, right, because I-56 already is the maximum stability, maximum binding energy per neutron. You go and fuse it to become bigger, or you fission it to become smaller, right, will drop the binding energy per neutron, which therefore means that you need to input energy into the system. So I would say one marking point is this one. This is one marking point. And then this is kind of like the second marking point here. And there's an input. Okay, so this one, the last one here, this is your conclusion. This last one here is your conclusion, right? Okay, then we have this graph here. Okay, part B now. Okay, part B, we have a kinetic energy spectrum for beta particles being emitted in the decay of platinum 1992 gold 199. Okay, so it's a beta decay. And you see, this is very interesting because here, your beta, right? Okay, every reaction here, if every reaction should give you the same amount of energy release or energy input. Okay, so right here you see the alpha, right? It has a range of energy. Your beta particle, right? It has a range of energy values. Okay, and most of the values are here. Okay, so you can see that there are different values of beta energy that's being decayed. Beta, remember, is just an electron. So that means this electron coming out. Remember, you start off with platinum, ET, okay? Then it leads to gold, okay? Then you have 1, beta particle shooting out. Okay, so when this beta coming out, right? So if this reaction is in theory, right, it should always give you the same value in terms of energy. In terms of this beta particle energy, right, it should give you always the same value. It should not have range in values. Okay, but because it have range in values, that means remember every beta decay here, right, will release the same amount of energy, which by right should all be carried in your beta particle. That means all of them should have the same amount of energy. But because it's not carrying the same amount of energy, that means some of the energy is escaping in another way. Okay. So next question they're gonna ask you, how does this tell you that, or how does, when you consider this, right, how does it tell you there's an existence of a neutrino? Okay. So basically we go by the idea that let's look at answer key for this one. Okay. So you have the total energy being released is constant, very important. So you start off with here. Constant release total, every reaction, you have every decay of the same amount of release. Okay, so then just how we say, if there are no other particles being emitted, all the beta particles share the same energy. Okay, but because there's a range, that means, right, there must be another particle to share the momentum. Okay, so in this case here, right, what this is saying is that, okay, instead of just these two gases right here, instead of just AU here and then beta here, one goes here, one goes here, right? Okay, so remember, we must have conservation of momentum. What this is actually saying is that, okay, I have gold here. Okay, gold may move a little bit this way. I have beta here. It might go this way. There must be another particle called the neutrino here that will go this way. Okay, so when you introduce another particle, right, your beta can take on different kinetic energy values. It doesn't have to have the same kinetic energy value because some of the energy can be carried away in the form of the neutrino. Okay, so in order for neutrino to carry energy, neutrino must have a mass. Because this one, if you have Ke of neutrino, right, this tells you that mass of neutrino, right, is more than zero. Cannot be zero. Okay, because at zero, you can't carry Ke. Okay, so 3 marks. Let's look at the mark scheme again to see what they want. Yeah, so this is the first point, and then this leads to the second conclusion. Two things. The last one is just the start, then therefore the conclusion. I would say the last one is not a mark point. I would say that you have one here, total energy is constant, that's one. If there are no particle or beta particle should have same energy, second one. However, there's a range of values. Okay. Those three things. These are three things I'm looking out for. Okay. And this one a bit more. Yeah, so I think the way to look at nuclear, if you can't really fully understand, is that basically your energy needs to be carried away somehow. Yeah, if you have a range of values, means that there must be some other thing that is carry away energy. Okay. Nuclear is not super difficult. It's doable. Okay. So now, okay, again, this is to calculate. Now we're using mass defect to work out the decay. To work out energy released during the decay, right? So we have the masses, then we can solve it. So we want to use E equals to delta M C squared. So this one is given in the form of what they want us. They want in joules, right? Okay, so let's find joules. So this will be, which is the product, bismuth. So this will be, okay, let's write it down. Okay, mass of bismuth minus away mass of thallium minus away mass of helium. Okay, times 1.66 times 10 negative 27. Okay, then multiply by 3 times 10 power 8 square. Okay, so let's work it out. Okay, so let's see. So 211.9459 minus 207.9374 minus 4.0015. Key in all the decimal place, don't round off, okay? For nuclear, don't round. Why is it? Wait, did I do anything wrong? Product, helium, I think I key something wrong here, right? Two 211.9459 minus 207.9374 minus 4.0015. I get 0.007. Okay, multiply by 1.66 exponential negative 27. Okay, and times 3e8 squared. Okay, so I get 1.045468 times 10 negative 12, right? Negative 12 joules. Round the answer off to 1.04 1.05 will do actually. Okay, but if you cancel 1 to 4 SF in this case, I think this is okay lah. Okay. Okay, so this is what you have. All right. Then they gave you this reaction. I believe we have done this question before. The next one here. Okay, I think we have done this question before. So we're just going to go faster. So this is for alpha decay, right? I can show that the ratio of Ke of alpha to K of daughter nucleus is given by 0.25A, where A is the original neutron number. So show that the energy of alpha in the reaction in C part 1 is 6.4 MeV. Okay, so let's start this one. So let's write, this is Ke alpha, Ke of this one, in this case, this is thallium, right? Thallium pH. Okay, and this is equals to 0.25. What is the alpha number for what's the vessel? 212. 212 minus 1. Okay, so 212 minus 1, I think this is 0.25 times 212 minus 1. So it's 52. 52. So that means your Ke alpha, so total here, there are 52 parts plus 1 part. So Ke alpha is taking 52 over 53 of the total energy. So 52 over 53 multiplied by 1.05 times 10 negative 12. Okay, so do that conversion. So 52 divided by 53. 52 divided by 53 times 1.05 e negative 12. Okay, this value you get. Okay, then convert it into mega electron volt. So divide by 1.6 exponential negative 13. Okay, so about 6.438. 6.438 MeV. Therefore, 6.4 MeV. Yeah. Okay. So in practice, alpha particle is found to have a kinetic energy of 6.1 MeV rather than 6.4 MeV as calculated. Suggest in this case why thallium and nucleus do not move off in opposite energy. So instead of carrying 6.4, it carries 6.1. We carry 6.1, that means, okay, let's say you only carry, so that means by right, thallium over here, alpha over here, right, it should just go opposite direction. Okay, but because now there is some energy left over, right, that means there must be some photon coming out. Photon, in this case, 0.3 MeV. This has 6.1. So if this is the case, right? This photon here also has momentum. If it has momentum, right? For conservation of momentum, these two cannot be collinear already. Okay? So you can look at the answer given. So this one, I think we talked about it just now, so don't go too much on it. Okay? Alright. Bismuth. Okay, so next one. Radioactive source contains N nuclide of bismuth 212. After 2 hours, bismuth reduces 0.25 N. But however, okay, although bismuth decays to form Thallium-208, Thallium nuclei number is less than 0.75 N because Thallium has also undergone decay. Okay, so by right, if you convert bismuth, will only convert Thallium. But then it doesn't mean that Thallium will not decay on its own. If Thallium further decays to something else, right, then you're going to have less Thallium than expected. Okay, so this one, I think just here. Over here, much shorter half-life. Okay, so Thallium will decay at the same time as well. Okay. All right, next. Calculation for this one, I think is quite straightforward. You can work out number of nuclide first. You want to work out N naught first. So N naught is equals to basically take the mass. So mass divided by molar mass multiplied by Avogadro lah. So this is 10 kg. 10 kg is 10 times 10 power 3 grams. Then bismuth 209 is 209 grams. Okay, times 6.02 times 10 power 23. Okay, like that. Okay, so this is the number of reactants. Okay, so you want to find likely to disintegrate in the next 100 years. What I do is that, okay, at any point of time, right, you have N. Okay, N equals to N naught E negative lambda T. Okay, so this will give me the number here. So basically, what I'm trying to find here, I want to find what is delta N. Delta N is equals to N naught minus N. This is equals to what? Okay, so that means I take this reaction here. Okay, I want to find N, right? So N equals to N naught you sub in. Lambda here, remember lambda is given by what? Lambda decay constant is ln 2 over half-life. Okay, so this will be, what's my half-life? Okay, so this one here, ln 2. Okay, the half-life I can keep in the unit 1.9 times 10 power 19 years. Okay, then the answer here will be in terms of per year. Okay, then once I have this, I sub here, right? So I want to find, okay, I find N over N naught is equals to E negative lambda over T. You note that this unit here, right? This one, let's label it out. This one is in terms of per year. This one, therefore, will just be in terms of year. They don't have to convert units to seconds. Don't bother. Okay, then go and solve. Go and find N first, then you can go and take N naught minus N to go and find the number of nuclei that were least unlikely to decay. Here, this disintegrate basically means decay in this context. Okay, mental break, pause. 2 minutes. Then I'll think first. Can I restart in 1 minute time? Okay, let's restart. 6 we are not doing, right? Okay, B. We're doing 6B. So I think I skip the photoelectric effect one. So we do the X-ray one. Okay. So this is the X-ray lah. So basically I will the filament here. So this is a full setup. Okay, you have your high voltage here. This guy here is negatively charged. So it will cause for the electrons to be emitted across. This end is the target metal is positively charged. So this is negative, this is positively charged. So electrons will accelerate this way. Okay. So then you get the graph. You collect once you have an X-ray being emitted, right? You collect the X-rays, photons, and then you plot this graph. So this is now we are plotting against frequency. Be careful. The earlier one was in terms of your wavelength. So it was a mirror, kind of like mirror image. Okay. So explain why there's a maximum frequency as shown in figure 6.3 because your electrons have maximum energy. And then this maximum energy, when the electron loses energy completely, right, it will emit a photon with the largest possible amount of energy and therefore maximum frequency. Okay, so this one not going to spend too much time talking about it. It's over here, I think. Somewhere here, I think. Yeah. Okay, so maximum energy loss. Okay. Then determine the maximum energy of the photons emitted. So from this one, we can find from the graph 8.0 lah. Okay. So we have E max equals to HF max. So 6.6 P times 10 negative 34 multiplied by 8 times 10 power 19. So this is fine. Okay, sketch from the graph. A graph sketch of figure 8.6.6.3, a graph to show if the variation if the current changes. Current here, this is about number of photons per unit time. Number of electrons per unit time. It does not affect the energy of the electrons. Okay? So it does not affect energy of electron, right? Your P graph, right, takes the same shape. Exact same shape. Yes, trace down. That. That. Oops, sorry. Exact same shape. Okay. So no loss, there's no difference. Okay, Q, if I reduce my accelerating potential to half of its original value. Okay, so I decrease half original value. That means remember my accelerating potential is EVA. EVA is equals to KE max of electron, which is equals to HF max of photon. Okay, so if this cuts by half, this will also drop. This will also drop by half. That means if I cut my accelerating potential by half, the total maximum energy, the maximum KE of my electron will be half. The maximum energy of photon will also be half. If it's half, this graph cannot go beyond this point here. It cannot go beyond this point. Okay, then now the thing is that do these peaks go back as well? Do they end up looking something like this? And then coming back to here. Okay, so remember I said these peaks are basically used to identify the metal. They correspond to the difference in the energy levels in your metal, right? You cannot shift these peaks because the metal has not changed. The metal stays the same. So if there is to be a characteristic peak, right, it has to be at the same position here. You cannot shift this. So this graph will end up becoming something like this. We're using the color to draw. You just go like that and then drop back down to here. That's it. This is Q. Okay, there will not be any characteristic peaks because characteristic peaks occur at a higher red value. Okay, that's Q. Okay, moving on. Okay, show highest energy. Okay, so these are the five lowest energy level hydrogen atom. You're given the values there. Don't memorize the values. Okay, then heat up. Okay, so hydrogen atoms are contained in a low pressure vapor lamp. So they are separated from rest and then bombard the hydrogen atoms. Then I get 436 nanometers. Describe energy, reduced energy level used to produce this wavelength. So I have E equals to Hc over lambda. You just do the conversion. So 6.63 times 10 negative 34. Speed 3 times 10 power 8 divided by 436 times 10 power negative 9. Okay, then I can work out energy level. Then this energy level, let's see, I think I calculate this way. Okay, so 6.63 exponential negative 34, sorry, 34 times 3E8 divided by 4.436 exponential negative 9. And I get this amount of energy, but I want it in electron volt, right? So I divide by 1.6 exponential negative 19. I get 2.85 MeV. Okay, so I'm looking for a change that give me 2.85 MeV. Yeah? And the best one here happens from where to where? E4 to E2? Looks like it. Which answer? I think it's E4 to E2. Or E2. Yeah, E4 to E2 is the best answer here. Okay. Good. Okay. Then explain the minimum value of V used to give rise to a transition in one. V potential difference. State explain the minimum value of V. How will you give rise to a transition point? 436. That means I need to excite it up to at least this level here. Okay, if I want to have E4 dropping to E2, right, I must first cause it to come to here first. Okay, but minimum energy, it could already be possible for it to be here. Lowest energy, yeah, all state. Not very sure. 113.6. Yeah, so start from ground state over here. Yeah, because I was thinking, do you assume that they're all at ground state? What if they are here? But because I think low pressure vapor lamp, I guess. Yeah, so you need to give it enough energy to go up first, to here first. Need to give it this amount of energy first before it can make this transition for you. I'm tired today. Okay, this is the last one already. I think it's more. Oh my god, why I pick such a long question? Okay, so you have beta decay, state origin of the beta particle. Beta particle is a neutron breaking down to give you a proton and electron. Okay, so this one is quite the nucleus. Okay, so one neutron breaking down to give you one proton and one electron. The electron becomes the beta. Okay, so if you go on to do more nuclear physics and stuff, you will know that there are three ways of producing beta. There's also electron capture as well. Okay, not going to talk about that, but yep. Right now equation representing the beta decay of Bismuth. So So this is 210 83 smooth, undergoing decay. Remember, neutron is converted into proton and electron. So so um, total proton count increases. This becomes 84. But because neutron converted into proton, right, the total number of nuclides stays the same. The total number of nucleons stays the same, right? So this is polonium, okay, and plus beta. You can write as electron now. You can write as like that. You can write as this. Okay, that's fine. Okay, or you want to, you can write as beta. Okay, both for both. Okay, so this one can be represented as beta as well. Yeah, use another color lah. Uh, yeah, so two ways of representing. State two quantities that are conserved in any radioactive decay process. Radioactive process. Nucleon number lor. So number of nucleons. That's one. Okay, next. Number of, okay, then mass energy. Okay, so two things I think. I will check answer for this one. Total momentum, yeah. Total momentum, total mass energy, nucleon number, total atomic number all same. Okay, don't accept number of protons and electrons. Yeah, because you won't have conservation of protons because total charge, proton number stays the same. But because protons can be gained from beta decay. So the total number of protons is not conserved. Okay. Now I've been dying to try. Finish. Okay, then we have mass defect calculation. 1.767. Okay. So this one they give us the numbers, then we can find Bismuth 209. Okay, so they give us some stuff. So mass defect. Let's find mass defect. So mass defect here is mass of bismuth minus away mass of polonium minus away mass of, so that's way. Give me the full things that I need. Hmm. Wait, wrong. This one is for mass effect of, okay, this is talking about delta M of this move. So what I do is that I will take uh total mass of proton plus mass of neutrons minus away mass of bismuth. So bismuth has 83 protons, right? So 83 times 1.00729 plus 210 minus 83, number of neutrons times 1.00867 minus away mass of bismuth 209.939. Okay, so let's enter this in. So 83 times 1.0072729 plus 210 minus 83 times 1.00867. 1.00867 minus 209.939. 1.767. Okay, so this is fine. 1.6, 2 marks, fine, nice. Okay. Then calculate binding energy in terms of MeV per nucleon of this one. So find binding energy first. So binding energy is basically mass defect multiplied by C square. So this is 1.767. 1.767 times 1.6 times 10 negative 19 times 3 times 10 power 8 square. Okay, you get this in joules, then convert into MeV. Okay, so yeah. Okay, so answer times 1.6 exponential negative 9. Eh? Wait, I wrote something wrong here. So this one is 1.66 times 10 negative 27. 1.66 exponential negative 27 times 3e8 square. This is energy in terms of joules. Okay, then convert to MeV. So divide by 1.6 exponential negative 13. I get 1650 MeV. 1650 MeV. Answer 1650 MeV. E? Oh, what did I do wrongly? 2.64 times 10. Yeah, I do wrongly here. 0.64. Where's the mistake? Try again. 1.767 times 1.66 exponential negative 27. This will give me mass in kg times PE8 squared. 263. Okay, then divide by 1.6 exponential negative 13. 1649. Okay. Buying energy. Oh. I know why. Because this is buying energy. But I need to find buying energy per neutron. So therefore, BE over A is 1650 divided by 210. So 1650 divided by 210, I get 7.857. Okay, yeah, now it's correct. Okay, so 7.86 MeV. Okay, and same thing, this one, similar to just now the previous part. So I'll just skip this one. And this one I never thought about it. Are we okay? Do I need to go through any other questions? Anyone? So look at the last question. Last question. This one is basically electrons behaving as a wave lah. So you're gonna have photoelectric effect happening here as well. Not photoelectric effect. Diffraction grating. Carbon film is acting as a diffraction grating here. Okay. What else? So just quickly skim through lah. Then yeah. So identify two features in figure 7.3 that shows wave nature. Okay. So you have figure 7.3. You have diffraction rings. What else do you have? 7.3. 7.3 diffraction ring. Yeah, pattern spreading over diffraction. Constructive and destructive interference. So the spread is one lah. Okay. And then you have your interference patterns for me. The rest of stuff I think quite straightforward. Momentum, this one, this is just using your kinetic energy one. Okay. Then from there you can find lambda equals hp to get your de Broglie wavelength. Okay, then after that, then I think this is again quite straightforward lah. Okay. So this one, if you increase potential difference, you will basically increase kinetic energy and therefore increase the momentum. Increase momentum, lambda h over p, the wavelength will decrease. Okay, then see what happens. Then follow your diffraction, your interference rules. Okay. Okay. I think we stop here. Anything else? Okay, if you need a book consultations, please go and book. I think once you start your papers, you won't have much time. So just yeah. I think the slots, my slots are updated, so you can see what you need lah. Okay, if you want to come in pairs, come in shows, I think that's fine. Just let me know in advance. Okay, the slots will basically expire within 24 hours of the intended booking. So let's say you want to book for tomorrow. You say you want to book, right? You cannot book anything before tomorrow 10:50. So maybe because it will close already. Okay, so this gives you some reaction time. But of course, you got last minute stuff you want to text whatsoever, so you can do that. Okay, that's all I have for you. Thank you.